So we have another example here of a line integral given to us in this more differential type form. So let's go ahead and take a look. First of all, I would be considering this to be of the form integral over c of m dx plus n dy. Okay, and so here is my m dx, and here is my n dy. And so thinking about having the opportunity to use Green's theorem, let's take a look at, first of all, our region. So our region is a circle of radius 3 centered at the point 5, -7. So we're going to say that that's the point 5, -7. Whoops, I don't know where my point went. 5, -7. And that we have a circle of radius 3 that is surrounding that center. So there's my circle C. And then, of course, the region that's being talked about in Green's theorem is the interior of that circle. So let's start thinking about the hypotheses or assumptions of Green's theorem and how they might apply to this particular problem. So our hypotheses. So first of all, we need that our region R, again, here is my R inside this circle. Whoops, where'd my circle go? Let's try that again. My region R is inside that circle. Okay, my region R is simply connected region. Yeah. Bounded by a piecewise smooth curve C. And that curve C, I can certainly orient counterclockwise without any difficulty. So we'll just put a direction on that curve. And so here we go. So R is simply connected region, bounded by a piecewise smooth curve C, oriented counterclockwise. So definitely we have the first hypothesis for Green's theorems satisfied. Let's take a look at m and n. So as I look at m and n, I see that m is a polynomial minus an exponential where I have a trig function inside my exponential. So that seems a little odd, but in terms of continuity and partial derivatives, let's think about what might happen here. So derivative of a polynomial is a polynomial, so that's good. That's easy to deal with. The derivative of an exponential is an exponential. So, and exponentials we know are nice and continuous. Okay, and when I use the chain rule to take the derivative of my exponential function, so e to the sine x, when I use the chain rule, I'm going to have e to the sine x times the derivative of sine x, which is cosine x. Also, very continuous, nice, smooth, well-behaved function. So, as I consider taking partial derivatives of m, it looks like everything is going to be nice and continuous in terms of the partial derivatives. And as I look at n, the same thing's going to happen. I've got a polynomial and sine functions. Sine functions are nice and continuous. So when I look at this and I think about m and n have partial derivatives. And I don't have to actually find those partial derivatives unless I need to. Derivatives that are polynomial. I'm going to abbreviate polynomial, exponential, and sine functions. Sine slash cosine. So I'm going to put a cosine in there, my apologies. Sine and cosine functions, all of which are continuous on any region. Are continuous on any region. Okay, so we see that we've satisfied the conditions for applying Green's theorem. And I suppose maybe you're a little concerned about what you're going to do with that circle of radius 3, but let's go ahead and take a look at how this might play out. So, because we can apply Green's theorem, so we had the integral over c of 7y minus e to the sine of x dx plus 15x minus sine y cubed plus 8y dy. And just to make sure we annotate it here on this screen, we call this m and we call this n. Okay, so we can apply Green's theorem, which means that this integral that we have here is actually equal to the double integral over our region, the inside of that circle, partial of n with respect to x minus partial of m with respect to y, dA. So let's go ahead and take a look at these partial derivatives that we need here. So if I look at n, and I want to take the partial derivative of n with respect to x, well, my first term in n is 15x, so the partial derivative of that term would be 15. And I look at my second term, there is no x variable. So as I do the partial derivative with respect to x, that remains constant. So I could say 15 minus 0, or I could just say 15. Now, the partial of m with respect to y, we need, and so let's do likewise. Let's look at m. And in m, our first term is 7y, so the partial derivative with respect to y is 7, minus the partial derivative of our second term with respect to y, and notice that the only variable in our second term is x. So partial derivative with respect to y of that term would be 0. So my partial of m with respect to y is 7. So this integral that I have representing the work, it is double integral over my region of 15 minus 7 dA. 15 minus 7 is 8, and I'm going to pull that in front. And what I'm left with is 8 times the double integral of 1 dA. Now we're going to be a little smart here because we know that our region is a circle. Our region is a circle of radius 3. And this integral represents the area of that region. Or of that circle. So I get to kind of take a shortcut here because really that integral is just saying it's 8 times the area of that circle, and the area of that circle of radius 3 is pi r squared, or pi times 3 squared, which is going to give us 72 pi. And this would be square units if you knew what the units were.